Welcome to this explainer. Look, if you're tackling the Cambridge Computer Science 9618 syllabus, you already know that implementing stacks using arrays isn't just a random topic. It's absolutely crucial. Why? Because it literally shows up in every single examination series. You can't avoid it. So today, we're tossing out the standard textbook reading. Instead, we're opening up the examiner's playbook to figure out exactly how you can lock down those top-tier marks.
Our strategic roadmap for today covers 5 key areas. 1. Core principles in architecture. 2. The procedural framework. 3. Top 3 examiner warnings. 4. Mastering comparative evaluation. And 5. The method mark strategy. Let's jump right into Section 1. Core principles in architecture. Thinking like an examiner. Right off the bat, there's a massive glaring difference between your standard candidates and your top-performing candidates. Standard answers usually rely on superficial breadth. Just throwing a bunch of isolated facts about arrays and stacks onto the paper and hoping something sticks. But the top candidates, they show analytical depth. They don't just memorize that a stack pointer stores the index of the top item. They know the causal relationships, like exactly why and how that pointer has to be updated before pushing or after popping data within a specific array architecture. That deep, precise understanding is what lets them tackle totally unfamiliar exam scenarios without breaking a sweat. And here is a secret straight from the principal examiner reports. If you want those significantly higher marks, you need cross-topic connections. You can't just treat implementing stacks using arrays as this isolated little island. It doesn't work that way. You need to show how it connects. How does your stack implementation impact memory management? How does it change the efficiency of an algorithm? When you weave stacks and arrays together with other parts of the 9618 syllabus, examiners notice. That's when they see true mastery. All right, moving on to Section 2, the procedural framework, a standardized sequence. Think of your exam approach like a high-stakes Formula One pit stop. Every single step has to be flawlessly executed in the exact right order. Step 1, deconstruct the question. What command words are they actually using? Step 2, extract the relevant data. This is where you pull out specific states from binary representations. Step 3, select your analytical framework. Step 4, execute with clear notation, meaning do your calculations and draw solid evidence-based conclusions. And finally, Step 5, present your answer using the correct terminology. If you memorize and run this 5-step sequence every single time you see a problem, you'll save time and completely avoid misinterpreting the question. Next up, Section 3, Top 3 Examiner Warnings, Navigating the Pitfalls.
We actually went through the principal examiner reports to find out where things go wrong. And we found exactly 3 critical mistakes. These are the major pitfalls that constantly cost students their grade boundaries, year after year. So what are they? First up, vagueness. Examiners despise vague answers. They don't want general descriptions, they want the specific technical details about your stack pointers, base pointers, and array indices. Second, forgetting boundary conditions and edge cases. Seriously, are you checking for stack overflow? When you try to push data onto a stack that's already completely full, or underflow when you try to pop data off an empty stack. You absolutely have to check those edge cases. And third, ignoring the context. If an exam question is specifically asking about a stack of print jobs, well, your variables and your logic better be talking about print jobs, not just repeating a generic textbook example. Lock your answer into their context.
Which brings us to Section 4, Mastering Comparative Evaluation, Critical Analysis. When you get to the high-level critical analysis questions, you can't just say solution A is good and solution B is bad. That's not going to cut it. You have to systematically evaluate multiple solutions side by side. What are the specific similarities and differences? What are the exact trade-offs when it comes to memory overhead or processing speed? For example, what are the limitations of using a fixed-size static array versus a dynamic structure? Analyze the trade-offs, acknowledge the limitations, and back up your decisions with hard evidence. That is how you secure the maximum points. Finally, Section 5, the method mark strategy, the ultimate failsafe.
I want you to pay close attention to this direct alert from the Cambridge examiners. They said, students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. This is your ultimate safety net. When you're designing algorithms or implementing array solutions, document everything. Write down your logic. Map out exactly where those stack pointers are moving, step by step. Because if you make some silly little arithmetic mistake at the very end, but your documented process is crystal clear, you're still going to capture those crucial method marks. So what's the big takeaway here? How are you going to apply this 5-step procedural framework and actively prioritize those tricky edge cases in your next past paper practice?
Next time you sit down to study, I challenge you to obsessively show your working and rigorously check for overflow and underflow. Make it your goal to capture absolutely every single mark available on the paper. Thanks so much for hanging out with me for this explainer. Now go crush that exam prep.